Our story begins in the 18th century with a radical idea posed by John Michel and Pierre-Simon Laplace. These men, pioneers of their time, dared to challenge the known boundaries of science and astronomy. They dared to ask an audacious question. Could a celestial body be so massive, so overwhelmingly powerful, that not even light could escape its gravitational pull? In an era where Newtonian physics ruled the scientific discourse, such a thought was revolutionary. It defied the very essence of what was understood about the universe. It was a bold step into the unknown, a leap of faith into a realm of cosmic mysteries. Michel and Laplace weren't just playing a game of imagination. They were laying the groundwork for a new understanding of the cosmos, an understanding that would encompass the strange, the extreme, and the unimaginable. Their concept was based on the law of universal gravitation, which states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. They reasoned that if a celestial body was sufficiently compact and massive, the force of gravity would be so strong that nothing, not even light, could escape. This was a groundbreaking idea. It was a concept that challenged the very fabric of the universe as we knew it. This theoretical concept of a dark star was largely ignored and forgotten for almost a century, lost in the annals of scientific history. It wasn't until the 20th century, with the advent of Einstein's general theory of relativity, that the idea was revisited, refined, and eventually confirmed. And so, from the minds of two 18th century scientists, a new phenomenon was born. A phenomenon that would forever change our understanding of the cosmos. A phenomenon that would come to be known as the most mysterious and intriguing objects in our universe. This was the theoretical birth of what we now call black holes. To comprehend black holes, we must first dive into the realm of gravity, an invisible force that gives weight to physical objects and causes them to fall towards each other. Known for keeping our feet on the ground and our planet orbiting the sun, gravity also plays a pivotal role in the birth and life of black holes. Picture an apple falling from a tree. This was the scene that sparked Sir Isaac Newton's musings on gravity in the 17th century. Newton proposed that every object in the universe attracts every other object with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This was a revolutionary idea that laid the groundwork for our understanding of gravity. Fast forward to the early 20th century and we find Albert Einstein, whose theory of general relativity refined and expanded upon Newton's work. According to Einstein, gravity is not simply a force, but the warping of space and time around massive objects. Imagine a bowling ball on a trampoline causing it to sag. A marble rolled across the trampoline would curve towards the bowling ball, not because of an invisible force, but because of the shape of the trampoline itself. This is a simplified way to think about how gravity works in our universe. Now, let's apply these principles to black holes. A black hole is a place where a massive amount of matter has been squeezed into a tiny space. The gravity is so strong because the matter has been compressed into such a small space that nothing can escape from it, not even light. The edge of the black hole, the place beyond which we cannot see, is called the event horizon. Consider a star 10 times more massive than our sun squeezed into a sphere approximately the diameter of New York City. The result is a gravitational field so strong that nothing can escape its pull. This is the reality in a black hole. In these extreme environments, our understanding of gravity is pushed to its limits, and gravity's playground comes alive. At the heart of a black hole lies the singularity. This isn't just a fancy term for the center of a black hole. It's a threshold where the laws of physics as we understand them break down. In a singularity, matter is condensed into an infinitely small, infinitely dense point. Picture it this way. Take all the water in the world's oceans, then squeeze it down to the size of a sugar cube. That's the kind of mind-boggling density we're talking about. But even that falls short of the reality of a singularity. The singularity is shrouded in mystery, and for a good reason. It's hidden deep within the black hole, beyond the event horizon, where no information can escape. This makes it impossible to observe directly. But by studying the space around black holes, scientists can infer the existence of these singularities. Now, what happens inside a singularity? Well, that's where things get really strange. According to Einstein's theory of general relativity, space and time as we know them cease to exist. In a sense, within the singularity, space becomes time and time becomes space. In other words, if you were to fall into a black hole, you wouldn't hit the singularity like hitting the ground after a fall. Instead, you'd be stretched and squeezed into it by the immense gravitational force, in a process rather ominously known as spaghettification. But here's the kicker. The singularity doesn't just bend the rules, it breaks them. The laws of physics that govern the universe outside black holes simply don't apply inside the singularity. This has led to a fascinating conundrum in physics, pitting Einstein's theory of relativity against quantum mechanics, the theory that explains the behavior of particles on a microscopic scale. So, what's the truth about singularities? Well, the jury's still out. But one thing's for sure, they represent the ultimate frontier of our understanding of the universe. In the heart of black holes, in the grip of singularities, time itself kneels before the might of gravity. Encircling the singularity is the event horizon, a boundary where the escape velocity surpasses the speed of light. This is the point where the gravitational pull of a black hole becomes so inescapable that nothing, not even light itself, can break free. It's the cosmic equivalent of a waterfall's edge. Once you tumble over, there's no swimming upstream. The event horizon is the threshold of the unknown, a cloak that hides the black hole's singularity from the rest of the universe. It's the point where our understanding of physics becomes less of a guide and more of a hopeful suggestion. As we approach this boundary, the laws of space and time start to twist and contort under the immense influence of gravity. But what does it mean for something to cross the event horizon? Well, from the outside, it's a bit of an optical illusion. Due to the intense gravitational pull, light from the object gets stretched out, a phenomenon we call gravitational redshift. So, as an object approaches the event horizon, it appears to slow down and fade away, never quite seeming to cross that boundary. But from the perspective of the object itself, it crosses the event horizon in no time at all, plunging into the black hole's unknown interior. Now here's a mind-bender for you. The event horizon isn't a physical barrier. It's a point of no return defined by the black hole's mass, spin, and charge, creating what's known as the Schwarzschild radius for non-spinning black holes, and the Kerr radius for those that spin. However, the real mystery lies beyond this point. What happens inside a black hole stays inside a black hole, thanks to the event horizon. It's a veil that nature has drawn around her most profound secrets, a veil we're yet to pierce. And yet, the event horizon is our ticket to understanding these cosmic curiosities. It's where the black hole's influence is most noticeable, where the drama of cosmic destruction plays out, and where we see the most direct evidence of a black hole's existence. Crossing this cosmic border means a one-way trip into the unknown. But even as we stand on the precipice, peering into the abyss, we can't help but be drawn in, captivated by the mysteries that lie just beyond our grasp. Engage your cosmic curiosity, because not all black holes are born equal. This vast universe of ours is home to a variety of these enigmatic phenomena, each with its unique characteristics and captivating stories. Let's delve into this cosmic variety. First, we have the stellar black holes, the most common type. These black holes are born when massive stars, at least 20 times larger than our Sun, exhaust their nuclear fuel and collapse under their own gravity. But their modest size, about 10 miles in diameter, doesn't make them any less fascinating. Despite their small stature, they pack a punch with a mass up to 10 times that of our Sun. Next in line are the intermediate black holes. These elusive giants are thought to weigh between 100 to 1,000 solar masses. They are the cosmic middle children, larger than stellar black holes, but smaller than their supermassive counterparts. Their existence is a recent discovery, and they remain a topic of intense research. Finally, we reach the supermassive black holes, the true behemoths of the cosmos. These black holes, found at the centers of galaxies, including our own Milky Way, can hold millions, even billions of solar masses within their event horizons. These cosmic titans play a crucial role in shaping the galaxies they reside in and are key to understanding the large-scale structure of the universe. But wait, there's more. Theoretical physicists have proposed the existence of mini black holes and primordial black holes, remnants of the Big Bang itself. While these are yet to be observed, they open up exciting avenues for research and could hold answers to some of the biggest questions in cosmology. Each black hole, from the stellar remnants that pepper our galaxy to the supermassive giants lurking at the heart of galaxies, tells a unique story of cosmic evolution. How do we study these invisible cosmic behemoths? Black holes, by their very nature, are elusive, absorbing all light and allowing none to escape. They are darkness personified, and yet they are not entirely invisible to our scientific gaze. The key to unveiling these mysterious entities lies not in light, but in the ripples they create in the fabric of space-time, gravitational waves. These are distortions in the cosmos, much like the ripples created by a stone dropped in a pond. When black holes collide or stars collapse into them, they create these waves that propagate across the universe, carrying with them the tale of their origin. Advanced detectors on Earth, such as LIGO and Virgo, listen for these cosmic whispers, allowing us to study these distant and enigmatic objects. But gravitational waves are not the only telltale signs of a black hole. As matter spirals into a black hole, drawn by its immense gravity, it forms a swirling disk of superheated particles around it, known as an accretion disk. This disk shines brightly in X-rays, a beacon amidst the black, and can be detected by space-based observatories like NASA's Chandra X-ray Observatory. Moreover, when black holes devour stars, they belch out bright flares of X-rays, a phenomenon known as a tidal disruption event. These flares can be spotted from millions of light years away, offering us yet another window into the world of black holes. In a remarkable feat of human ingenuity, in 2019, scientists even managed to capture the first ever image of a black hole's event horizon, using the Event Horizon Telescope. This was a testament to our technological prowess and our insatiable curiosity to understand the universe. So while black holes remain cloaked in darkness, their influence on the cosmos is anything but subtle. Through their gravitational dance and their voracious appetite, black holes reveal their presence. They remind us that in the cosmic theater, even the invisible can have a starring role. While we've come far in understanding black holes, they remain shrouded in mystery. The more we learn, the more questions arise, a testament to the complex nature of these cosmic enigmas. One of the most profound mysteries is the information paradox. This theory, proposed by Stephen Hawking, suggests that all the information that falls into a black hole is lost forever. This is in direct conflict with the laws of quantum mechanics, which state that information in the universe must always be preserved. This paradox has puzzled physicists for decades, and despite numerous theories and debates, a definitive solution remains elusive. Then there's the concept of Hawking radiation. According to this theory, black holes aren't entirely black. Instead, they emit tiny particles, a phenomenon that eventually leads to their evaporation over an inconceivably long period of time. This idea, while fascinating, is still unproven as the radiation is far too weak for our current technology to detect. On the larger scale, black holes present another enigma, their role in the evolution of galaxies. Many galaxies, including our own Milky Way, harbor supermassive black holes at their centers. These cosmic giants can contain millions or even billions of times the mass of our Sun. But which came first, the galaxy or the black hole? The answer to this cosmic chicken and egg problem is still up in the air. Finally, there's the question of what happens inside a black hole, beyond the event horizon. This region is inaccessible to us, both physically and observationally. Does a singularity truly exist there? Or is there another reality, perhaps a gateway to another universe? These theories, while speculative, fuel our quest for knowledge. They push the boundaries of our understanding and remind us of the vastness of the cosmos. Black holes are more than just astronomical objects. They're cosmic riddles, waiting to be solved. Black holes continue to challenge our understanding of the universe. As we venture further into the cosmic abyss, who knows what other mysteries we'll uncover? From theoretical shadows to cosmic beacons, black holes have evolved from the realm of pure speculation to tangible objects of study. We've journeyed from the 18th century musings of Michel and Laplace through the twisted playground of gravity to the singularities at the heart of these cosmic giants. We've delved into the mysteries of the event horizon, explored the variety of black holes in the universe, and unveiled these invisible behemoths through the echoes of gravitational waves and the glow of accretion disks. Despite our progress, the enigma of black holes persists, with questions about Hawking radiation and the information paradox still looming large. These cosmic mysteries are not merely puzzles to be solved, but invitations to further our understanding of the universe. As we continue to explore, one thing remains certain. Black holes, in their captivating darkness, continue to challenge our perceptions, our knowledge, and our very comprehension of reality. Black holes continue to captivate and challenge us,